Hi everyone, welcome back to Math 256. This is Scott. Let's get started. Section 1.3 has to do with slope fields and solution curves. Alright, so here's what we're going to look at now. First things first, let's discuss the setup. We're going to be interested right now in a first order ordinary differential equation. So remember what that means. So the first order means first derivative. Only the first derivative is involved. Ordinary means that it's not a partial derivative, but it's a straight up derivative. So what we have here is just one function, or one variable as a function of the other, and so what we're going to have is a derivative of y with respect to x merely being some expression that involves x and y. No further derivatives. Okay, so that's the setup. But what this means, if you think about it, is then for every pair of coordinates, x and y, in other words, every point on the xy plane, we can find a derivative, in other words, a slope. So, this means we can associate a slope, which is the same thing as the derivative, we can associate a slope to each point. On the xy plane. So, an example here would be something like this. To take something relatively simple, let's say dy dx is equal to just x plus y. So what this means is every point will correspond to a slope, which is just its x-coordinate plus its y-coordinate. So we can represent the solutions to such an ODE, such an ordinary differential equation, via a slope field. Which is an array of line segments that represent the slopes at representative points. So here, we'll just sketch by hand one relatively easy case like this, and then we'll look at how to let technology do some of the heavy lifting for us. So let's say we had points like -2, -1, 1, and 2 for x, and the same for y. So we're just going to have a little lattice here. Little lattice of the various points around the xy plane coming to you at the integer coordinates from -1, sorry, from -2 to +2. So we got a bunch of little points here, and at each point we're going to draw a little line segment that's going to demonstrate the slope that we would get by adding the x-coordinate and the y-coordinate. So here we'd have -2 and +2, so the little line segment is going to have slope 0. The next one over, we're going to have -1 and +2, so it's going to have a slope of 1. Then we're going to have a coordinate of 0 and a coordinate of 2, so it's going to have a slope of 2. Then it's going to have a slope of 3, and then it's going to have a slope of 4. So I'm just estimating here the slopes. Now, next row here, we're going to have -2 plus 1. It's going to be a slope of -1. -1 plus 1, it's going to be a slope of 0. And then we have 0 plus 1, it's going to be a slope of 1, so it should be parallel to that one. This one is going to have a slope of 2, so it should be parallel to that one up there, so it's going to whatever, close enough. And then a slope of 3. And then over here, what we're going to have is -2 and 0, so that's going to be a slope of -2, -3. Sorry, I'm sorry, -1, what am I saying? 0, 1, 2, and then over here we're going to have -3, -2, -1, 0, and 1. And then finally here, -4, so it's going to be steepest down. -3, slightly less steep down. And -2, still less steep down. -1, least steep down, and then 0. Okay, as you can see, like most times when we do something by hand, it starts off fun and then it quickly gets old. So this is not going to be a common habit of ours to make these slope fields by hand, but it'll help us in this case to get the lay of the land. All right. Now, once we have this slope field, we can then try to figure out what the solutions to this differential equation would look like by just imagining kind of going with the current. Just imagine drawing something whose tangents at each point are consistent with the little line segments here. So then, we can sketch solution curves by just kind of going with the current. So just think of this as being like a little river, and what we would just do is just follow the path that these solutions are seeming to point you in. So something like that, something like that. Maybe one that's just going straight on down. Maybe another one that's going. Maybe and some down below here. That one is not very good actually because I didn't follow the slope at that point, but you get the idea. All right. And one note. Slope fields are also sometimes called direction fields, although direction fields is something that is a term we'll more frequently use for a different but related concept, which is going to happen when we're talking about systems of differential equations. But you will frequently see it. So fields. All right, but it's in the record now. Now, before we get into technology and we see what it can do for us, we have one more human task to do. So one more human task is to ask ourselves what people have been asking themselves for centuries. Do these differential equations which produce these slope fields, which produce solutions we can draw, like so, are we always guaranteed to be able to draw a solution going through each particular point in a differential equation? Well, this was one of the first major seminal questions asked by mathematicians studying differential equations, and they hammered out the following, which is one of the great triumphs. So, like most things that call themselves theorems in this class, we're not going to prove it. It's far too advanced for us to prove in here, but it is a subject of study. It's a subject of future classes in more advanced settings, and it is what's called the existence and uniqueness theorem. All right, so the existence and uniqueness theorem. So here's the setup. So what we have here is a first order ordinary differential equation. So dy dx equals f of x comma y. So just as we said earlier. But now some special conditions are going to be stipulated here for f, where f is continuous, as is the partial derivative of f with respect to y. So by continuous here, so those of you who haven't taken Math 254 and aren't necessarily as familiar with functions that have more than one variable, if we say a function is continuous, what that basically means is there are no abrupt changes, or there are no places where it's undefined. It will smoothly change. You give x a tiny change, f will have a tiny change. You give y a tiny change, f will have a tiny change, and it's always defined. Now, what it means here, the partial derivative of f with respect to y is basically saying that if you were to hold x steady and change y slightly, that'll give you the partial derivative, the rate at which the function changes as just y. Y itself is changed, and we're saying that that is also continuous. So there's going to be a smoothness to the changes, specifically in the y direction. So that's the setup that we've got here, and then and actually I should say it's continuous, as is that, on a rectangle which we'll call R. So it doesn't have to be continuous on the entire xy plane. There's just some rectangle within the xy plane for which this function and its partial derivative with respect to y are both continuous. And then, so further pieces of the setup here, the point a comma b, so that's x coordinate a, y coordinate b, is in the interior of R. So what it means to be in the interior of a rectangle is that it is inside the rectangle, but not even on the boundary. It is strictly within. Then, so that's the setup, and now, then, if this has been satisfied, then here's what we can say. There is an x interval I containing A such that the initial value problem dy dx equals f of x, y. So that's the differential equation part of the initial value problem, and then we still need an initial value, otherwise we wouldn't call it that. The initial value here is going to be y of a equals b. So there is an x interval I containing a such that the initial value problem, this, has not just a solution, but a unique solution. On I. All right, so what this all means if we were to look at it graphically is this. So not an example, just graphically. So here's the xy plane. Here's the rectangle R. Here's the point A comma B situated within the rectangle R. Here is here's the interval I, which here would correspond to the x values going from here to here. And what this is saying is basically imagine there was a slope field here, and containing this point right there, we could essentially follow the trajectories of the little line segments, provided that the function here was continuous, so meaning there's no abrupt change in these slope fields, nor even in the rate of change of the y's as we go over that. There's going to be some little solution here that is not only guaranteed to exist, but guaranteed to be unique. Okay, now that is just more or less interesting fact that it has been shown that this is true. But it's not something that we're going to dwell on a lot in this class because it's a little bit above our pay grade. But I want to just give an example of this failing. So here's an example of a failure. So let's take the differential equation dy dx is equal to y over x. Now, one category of function here that would be a solution to this is the following: y equals cx. So this is an example of a family of functions that would satisfy this. However, there's a point here that would be perfectly well defined for this function, but which would be catastrophic here. And that point will be when x equals 0. So at x equals 0, the function fails to be a solution because the differential equation isn't defined. And we'll actually see it gets worse. It gets worse than that, but we'll wait for the intervention of technology before we can really explore the cascading horrors of this particular point on this particular slope field. And now let's have a look at some of the technological tools we can use to make graphs of differential equations. So first, the TI-89. If you go into the mode screen on a TI-89, you'll see options for the graph that include number 6 here, which is differential equations. So we'll go to that, press enter, and then if you go diamond F1, that gives you the y equals screen, but now it's not just y equals, it's y prime equals, because we're talking about a differential equation. And notice that the x variable here is t, not x. So if I wanted to do x plus y, then that's going to give me, in this case, t plus y1. Now you do a y1 by just typing literally a y and then a 1. It's just y followed by a 1. And so you do that and you press enter, and that is the differential equation. And then the I here is for initial value. So the t naught is going to be the initial x value, and then corresponding to that will be the initial y value, y naught. So let's go ahead and put in a y naught of 0. All right, now go to F1, which is the Tools tab, and if you go down to number 9, just off the screen here, then we can make some adjustments to the format if necessary. So coordinates, you have two options on the coordinates. There are rectangular coordinates or polar coordinates, as you can see. And you got some options. You can give it a grid, you can turn on or off the axes. We can have a leading cursor, that's for the solution curve. It'll tell you where your initial condition was. You can have labels, and then the solution method. When it draws the solution curves, it has two choices of the solution method that it uses internally. So there is RK, which stands for Runge-Kutta method, and then there is the Euler method. In this class, we'll discuss what the RK method is like, but then we'll really delve into the details of Euler's method. But it doesn't really matter for our purposes right now which of these you're on, but we can just say the Runge-Kutta. And then for fields here, we have two options. Slope field, which is what we use if it's a single differential equation, or if what we're talking about is a system of differential equations, then we can have a direction field instead. So remember, sometimes direction field is used as a synonym for slope field. However, it is more specifically used for systems than for single differential equations. So there's that. Okay. Now, put it on slope field, because we're only talking about a single differential equation here, and then you can adjust the window by doing diamond F2, and that gives you various pieces to adjust. You can set the t step, things like that. For the actual solution curve is what that part pertains to. And then for the slope field, you can set the minimum and maximum x values for your window, the x scale, the y min, y max. -10 to 10 is fine for all these, and then we have some extra little pieces here. The field resolution, that's going to be how dense the line segments are. But let's now go back and take a look at the graph. So diamond and F3 will give us the graph. And what we have here is the slope field, just as we already drew. And now here comes the solution curve. Right now it's doing the positive values of t, and when it's done with that, when it goes up to a t value of 10, then there it goes. It draws the negative values of t. Okay, so there's our differential equation, and it's so in a slope field, and then that's that particular solution curve. All right. Now, let's put aside our calculator and see what the internet has to offer. To use the internet to draw differential equations, basically all you have to do is type into Google something along the lines of slope field generator, and you can see this isn't my first time searching for this particular thing, but if you just click this, essentially a bunch of equivalently good options all come up, and they're all pretty similar in what they can do. You just click on any of them and you can see here you can adjust what the differential equation is. You can adjust, right here, you can adjust the window. You can make some adjustments to the density of the slope field, so more or fewer, and you can change how long the line segments are. And you can change the step size. So very, very standard stuff there. And most differential equation plotting things will be very similar to this. Here's my particular favorite. If you go down a little bit further, you find the one from Bluffton University. This one has a couple features that are extra nice, and some of them are pretty much the same, but you can then make other, so later we'll use other pieces of this. We can do it as a system, we can do a polar ordinary differential equation, we can do a polar system. You can change the differential equation, you can change the window, you can increase the number of segments in each direction. We have the different options again for the method. It doesn't matter which one you choose really for now. And you can put in the initial curve, and there it is. Alright, so there's that, and we can clear it away. We can do another one. But what this one also has, put it back in, what this one also has, which we'll use later, we won't use it right now, but later on we'll use the option for numerical solution tables and time plots that it also has down here. So these are the actual x and y values that are generated by using whichever solution method you have selected. Now, let's clear away all these curves and try the differential equation y divided by x. So let's have a look at this one and see what's so problematic about it. So you'll notice the differential equation y over x makes a slope field where all the little line segments radiate basically out from the origin. Now, one thing about that is already, as we already mentioned, problematic, is that at the origin itself, this differential equation isn't even defined, or actually at any point where the x value is 0, this differential equation isn't even defined, so solutions here become a sort of meaningless idea. But aside from that, there's something that's even more problematic about this. So now that we can see the slope field, we can actually see this a little bit better. Now, imagine ourselves starting at some particular point, like say -1, 1. Now, let's see what this gives us when we hit this. So it gives you the line that goes through the point -1, 1, so right about here, and it just follows these line segments that radiate out from the origin. Now, right here you can see that this one actually happens to pass through the origin, which is bad enough. But here's the real kicker. Here's the thing that makes this a particularly pathological example. So the solution that it has drawn here is not only a little weird at this particular point, where it's not actually even defined in the differential equation, but it's not unique. So it was perfectly unique as we were moving our way down here, as long as we were within the rectangle of continuity for this particular differential equation. But once we got here, from this point on, we could go back out from the origin in any other particular direction, because all solution curves here, for whatever initial values, all the solution curves here all pass through the origin. So they all share that one point. So there's nothing even slightly unique about that particular trajectory once it has gone
once it has gone through the origin, it could just as easily turn and go any other direction from there. So that's a case of the existence and uniqueness theorem being violated. So the solutions here are not unique because they all pass through the origin. So from the origin, you could easily turn and go any particular direction. So that's why there's only a limited scope of uniqueness, only until you reach the end of the interval that is within the rectangle within which the function, that is your differential equation, is continuous and has a continuous partial derivative with respect to y. Excuse me. All right. So that's that, and join me next section for section 1.4 in Math 256. Till then.